Let's start with basic concepts on the load transfer, lateral load transfer, just like we did for the gravity load transfer. We now come to wind and earthquake. Both of them produce similar response, although their actual application is different, but both of them produce ultimately one common response, which is lateral movement. So we are concerned about now the lateral movement of the buildings. So now our main concern is lateral movement of the building and the effects that the movement produces on the structure. So we are going to go from the movement onwards. And now look at this one. Basically, wind load, as I showed you earlier briefly, is going to be something like this. So it's going to be wind pressure, and there's going to be structure, and then the wind load will vary with height. It's a pressure multiplied by the area, exposed area, and it produces force. It will produce two forces, one along the structure, one across the structure. Both of them make the structure move about the foundation. So and then we will have a roof displacement, which is going to be our one of the criteria. And the second one is earthquake. And earthquake will be a motion at the ground, which will then shake the structure. Inertia will come in, and inertia will actually start to move the structure, and will have the displacement. We normally differentiate between the roof displacement due to wind and earthquake. Normally, we have limits for that. We don't have limits for this one. We will talk about this as we go along. So in either case, it's the displacement, lateral displacement, that we are concerned with. We are going to go into more detail about the modal response and many things later. But for the time being, let's start with the basic displacement concept. Second thing is that displacement will produce forces, and those forces are now treated very differently. In wind, we treat those forces produced because of the displacement within the linear elastic range of the components. So we want every component in the structure to remain within the linear and elastic range of the structure without, should not say exactly linear, but before it reaches its capacity. So it's going to be force-controlled capacity that we are going to design our structure here. For the earthquake, we are going to let it yield, let it deform a lot, and then come to a level of force, which we will do. These two levels of force will be very similar for the purpose of design. The level of force between wind and earthquake design force level will be very similar. But the displacement at the two loads will be very different. And so we have to come back from the two. So this is the key difference. The displacements will be very different. Force level may be similar. Design force level may be similar. In fact, this is our design force level here. Wind will be roughly here. So normally wind is amplified to reach here. Earthquake is reduced to reach here. And we will talk about this later. Today is not the topic, but I'm just telling you that the displacement limits on the two will be very different now. Because for wind, we expect very small displacements. For earthquake, we expect large displacements, even though the force level may ultimately be very similar. So that will create different expectations from the structure because of this concern. Right. And ultimately, we have to satisfy these 10 criteria. I told you: stiffness, stability, strength, deformation, drift, ductility, damage, damping, energy, and acceleration. And I will start today with these two, deformation and drift, as our primary criteria, because if you control these, you will indirectly control everything else. So if you control the total roof displacement, which is deformation, and you control the drift, then everything else will most likely fall into place. So we will now start with these two parameters as our primary target for structural systems development. So first of all, you should know that there's a difference between the vertigravity and lateral load. I already mentioned a lot of that. You can read that. So now let's look at the lateral response. So when we have the lateral response, what will happen is that we have the forces coming from the side. They will produce vertical effect. They will have several effects on the structure. Some effects will be vertical, some will be horizontal, and then you can see here, then there will be the foundation forces will be generated, which is the uplift tilting moment. Compressive forces will be generated in the columns, tension and tensile forces will be generated, and then bending moments will be generated in each component, and then shear forces will be generated. So because of the deformation, you will have axial forces, you will have shear forces, you will have bending moments, and you will have foundation tilting moment or stability anchor forces to this one. So basically, lateral movement will cause these 3-4 types of things that we should need to be concerned with. They go back to our 10 criteria for stability, strength, and everything. So now, once we have the control on the lateral movement, we will be able to control all of them because they are all indirectly computed from the displacement, or they're interrelated. Now, this is very interesting observation, which we will start now going to the structural system behavior. This is an interesting observation. We are looking at a structure which is composed of, let's say, two very distinct substructure configuration. One is a frame type, which is beams and columns. Second is a truss type or a wall. We will see that wall and frame or truss are the same later. And then if we separate them out independently, the frame will like to bend like this. It will like to bend in the beginning a lot and then gradually straighten up. So it's a shear mode, actually, as you can see. So maximum displacement will be here, and then it will straighten up as it goes, or will become less and less and less. On the other hand, this one, the maximum will be at the top. In the beginning, it will be 0. So the two systems, the truss type system or shear wall system or shear system, I will go into detail, is going to be behaving opposite to a frame system, completely opposite. One has a flexibility at the top, one has flexibility at the base. So when we put them together, they start to interact with each other. One is pushing, one is pulling. Some portion, the frame is going to be pushing the wall, and some portion of the top, the wall is going to be pushing the frame. So there will be tension, compression on the floor when they start to interact. So this is called the frame shear wall interaction, level number 1. Level 2 we discussed later. So this is the basic difference, and I will go into more detail step by step, between the two types of structural system that exist. One is the pure flexural, we call this flexural system, and this is a axial system or shear system. So we combine them together, the building actual deformation becomes like this one, and it goes like this one. So now this is a combination of these two. And then you can optimize it by putting the bracings, distributing them in such a way that you get the optimum level here, because you don't need this bracing here. You might stop it somewhere, and you might need less and less. So this is the optimization of the structural system for deformation control. Just enough to get what we want, not too much, not too less. Because if you overuse it, you get a displacement which is less. Nobody cares about less displacement because they want cost to be reduced. So displacement, so a lot of the programs, a lot of the designs are drift optimized. So there are software, there are procedures that optimize the structure for drift. Some structures optimize for cost, some structure optimize for natural period. But then you basically, ultimately, for tall buildings, drift optimization or the displacement optimization is going to be the primary focus of our work. So any structural system that optimizes this will be very good. And now we can also see that if you let these are 3 columns connected by pin-ended beams, not rigid beams. These are just simply supported on the column, like a concrete column with a steel beam just connected, not moment connection, not rigidly connected. So if it is like that, these 3 columns will bend independently as 3 cantilevers, and beams will just move together with them. That means there is no frame, there's no contribution from the beams to the displacement. Entire displacement on drift is contributed by columns alone. This can never work in in a system that you only rely on columns to control the drift, it just will not work. So columns are very flexible. So if you continuously rigid frame, you will see that the displacement becomes that much less. And now this, which means when we put the beam into this one and we rigidly connect it, the displacement is now controlled by not column size, but beam size. So now if you want to control the displacement of the drift further, you increase the beam size. It's a misunderstanding by many people that if you have a problem with the drift, you can increase the column size to control that. No. Column size in a tall building will have almost no effect on the lateral displacement control. So increasing column size is pointless, it's useless. It is the beam which is going to play that part. And the problem with the beam is that people will not let you make it too big because, as I told you, people don't want beams anymore. There's a high headroom problem. Architects don't like it. Nobody likes beams, which means that we end up with this situation that we will have to develop systems which rely on columns with this system only for gravity, not for lateral, which means that we can add now system inside. And you can see here, if you just add some other system in just one floor, suddenly it affects. So that means the structure which is going like this, you just block one floor and suddenly it has a stiffening effect until that, and the structure becomes straight a little bit, and then it just alters the entire displacement above. Just one floor, if you make that floor braced or wall or whatever, we will see many things that can happen. So now we see that extreme case, only columns with pin-ended beams to a continuously rigid frame, to a rigid frame with bracing in some places. How many bracing we need? That's what I've mentioned, is the optimization. How many bracing you should put to get what you need? Where should we put it? What you exactly need, right? So that will be system development. So this is the second important basic concept that we want to talk about. And then you can put it at many locations, as you can see here, one location, 3, 4 location, all the bays in one direction. So every single decision alters the displacement pattern and the drift. This is actually showing, these 4 slides indicate that everything is in our hand. We are in charge of optimizing the structures, framing system, or structural configuration to get exactly the drift and the displacement that we want, because each intervention changed the displacement here. And size of this, and everything will change that. So which means that now it is us who have the control on the structural framing to control the drift and the displacement, which in turn will control everything else. Okay, that's this 4th important point. Now, based on that idea, we can go further. We can say this is a flat slab system with small columns that we talked about, right? This has no lateral resistance at all. That's why codes will not allow flat slab system, flat plate system for a tall building, because it just won't stand. So this is a starting base point, nothing, 0, quite close to 0 stiffness for a system like that. Then you make a rigid frame, it becomes a little bit better. Then you add a truss frame in the middle, or you add a wall. Both of them have nearly the same effect. I will show you in a minute. Similar. And you can make this bracing almost as effective as a wall, or you can model the wall as a bracing. Both is possible. And then you have a continuous shear wall like that. So the difference between this and this is that you have a beam passing through the wall. So it's a structural, it's a frame with the wall in between to block the frame. It's not the same as that, there is a single wall and beams are just connected at the end. The two have different behavior, different performance, and different placement characteristics. Whether we have a wall bracing inside a frame or we have a wall connecting to a frame. Because the connection of the beam to wall is not the same as beam to beam running through it, and you just put an infill wall and then so this is going to be more effective in general than this one. Okay, so this is just a little bit of further development of the systems, evolution of how we keep adding things. And then you can think about a very different approach completely. You say, okay, the building is moving. Why don't I just tie it down like a tower with the wires? Why am I worried about all of that? I just tie it down to the foundation, right? That's another extreme value, because you have, like, if you have a single, this one now comes in handy. If I have this one and it's moving, so one simple thing is just put two ties here and just lock it down like the towers, tied down towers. That will work, because then you have zero displacement or very small displacement. But the problem is that, once again, you can't have it. And now actually we have it. The Dubai Creek Tower is exactly that, right? Somebody said, okay, why not? Let's do that. But most often you will not do it. So them say, okay, because the space is not available, so they say, why don't we tie it like this one, right? Rather than two, you can move this tie here, same effect, and you reduce the base over there. Then somebody said, okay, why don't I just convert those ties into structural framing, right? Because it's a column. I can't have cables there. This form comes up, and then people do all kind of imaging. So you can see easily that from a simple concept sketch, people keep on coming up with more and more options and more ideas until they come with some very nice idea, and then you, oh wow, it was so simple. Why I don't think about it? Every time when we look at something, somebody's already done it, we say, oh my God, it's so simple. Why I didn't think about it? Because those people arrived at it after several trials and development of the system, not just arrived like that. People say the light bulb thing, but it doesn't happen like that. You have to work on things and understand concepts. So this is the tension column, or the diagonal bracing, or the diagrade concepts that develop on that, right? So now we can see clearly that deflection, lateral displacement control can be done in a number of ways. Let's get back to the numbers now. So we are looking at these two things now. We are looking at the frame with a total displacement D at the top, and we are looking at a interstory displacement delta between two floors. These are the ones that we will be talking about throughout the course. How much displacement at the top is allowed with respect to the total height, and how much interstory displacement, relative displacement between two stories relative to the height of the story. Those are the two indicators that you should get used to it for this course. The displacement ratio, which is the H over D, which can vary between 200 to 100 or even less, and the interstory displacement ratio, drift ratio, which normally represented in ratio or a percentage, could be 0.5% to 2%, can be up to 4% in extreme cases. Okay. 4% is very, very high, which is equal to H over D of 25, which is extremely large, right? But we use different indicators for different loads. For wind, we normally use the first one, and for earthquake, we normally use the second one. Wind we also use, but we normally control at the top. For earthquake, we control between two floors. And this ratio, interstory drift displacement, is not as simple as it really seems, because there is a tilting of the structure and there is a relative displacement of the two floors, not the same. So we're looking at the net interstory drift, not the total drift, which we will talk about how to calculate. You cannot calculate from displacement just simply like this one. Okay. Anyway, so these are the two things that we are going to now optimize or control. Every structural system ultimately will come to limit the H over D and limit the delta over H percentage, right? So let's see what happens if I take a very simple example and a simple structure. This is what I'm going to compare now. I'm going to compare a frame, a typical frame. It's a 7 meter, 3 meter something, and there is a truss. I just put some diagonal there, and I make a wall of the same height. Okay, and I'm going to apply the same load to all three of them and see what happens to these two indicators. This is a small structure, but it still tells us a lot. Okay, so when I do that, I find something interesting. Frame is 60 millimeter here, 48 millimeter here. as we expected. Most of the displacement happens in the first floor, then it becomes straight, as we showed earlier. So it's now proven that it's actually like that. This one is 3 millimeter, 1.5. It is almost in the beginning, so it's a linear displacement. It didn't change. And it's very small compared to that one. Even though I use almost the same material in both of them, I just reduce the beam size and add a brace. So the total material used in the two is nearly the same. And I compress all that material into a single wall, only 10 centimeter thick of the same total material, and you see only 1 millimeter displacement. So for this range, you can see that the frame is already too weak and wall is already very strong and truss is somewhere in between. Of course, if I change the truss diagonal sizes, the displacement may change. Now look at the H over D. H over D is 100 for this particular case, right? 2000 for this one and 6000 for that one. That means for this particular indicative case, the stiffness of this wall is 60 times more than the frame over there. Of course, if we have a wall, we cannot use this as a whole, but I'm just trying to tell you that the material distributed in the three is nearly the same, but the displacement here is extremely small, and stiffness, this is about 20 times more stiffer than that in terms of the displacement or the drift control. Okay, and the drift in the two cases is almost equal, both the cases. Here, drift is very large in the first one, small in the upper one. So which means that the frames have a huge drift problem at the lower floors. Okay, and secondly, their stiffness in general is extremely small compared to truss as well as the wall. Of course, this is a two-story building, but the story doesn't change. For very tall stories, then this will depend on many other factors, and we will talk about that. But in general, we can see that if you resist the lateral forces by axial and shear is going to be more efficient than bending. That's what we see from here. So if you look at the bending moments, there's a very large bending moment here, almost no bending moment here, because all of the force is taken by the diagonal forces. That means we converted the lateral force into axial forces, not in bending. Bending is reduced, and that's why our displacements are reduced, because axial stiffness is generally more efficient than flexural stiffness in deformation. And then shear is extremely, very, very, if you have a perfect shear panel, it's fantastic. So it doesn't deform much at all. It's almost rigid in a certain proportion. So that's the basic information that will help us now to move forward in understanding the behavior of various structural systems and also developing our own when we have a problem of displacement, drift, whatever, we try to now find one of these components to add into our system somehow or the other. Okay, so which means basic strategy should be to convert flexural load transfer to axial load transfer. This is something that I'm going to say many times in this course. Whenever we can convert bending behavior into axial behavior, you would be much better off, because as you can see, bending axial behavior is far more efficient than bending behavior. So bending is a killer for tall buildings. And wherever there's bending, we have to come back and find a way to convert that into axial or shear. But shear also has a limit, we will see later. Then shear load transfer and axial load transfer are interconvertible. So when you have a shear load transfer, that you have seen before, that this displacement, this one and this one are very similar. So if you have a shear, this is a pure shear load transfer, but if you put it in axial load transfer, it still works, because you replace the shear by an axial member, which is similar in concept. So it blocks the panel deformation. So then we have the same behavior. So which means shear behavior, pure shear behavior, and tension or axial is interchangeable. And we know it from previous course where we remember we converted shear into equivalent strut-and-tie model. We studied so much about that. We designed the shear based on the tension and compression stresses and forces, which means we know that shear can be easily converted into equivalent tension and compression system, right? So those are the two important lessons we learn from this discussion now, and these will become basis of our strategy for system design. Okay, let's move on. Second one is beat the math. Math is good, but we don't want to rely on math now, because if we only think about math, we are limited by math. We have to find a way that 1 plus 1 is not equal to 2. It is always greater than 2. We want to find a way to make 1 plus 1 greater than 2. And you will say, no, it can't be. It's a basic truth of the math. I said, okay, fine. For mathematicians, yes, but no, for me, no. 1 plus 1 doesn't have to be 2. It can be, and it should be more than 2. That's what we want to find. We are going to find that that's the efficiency of the system. How you put 1 and 1 together. How do you add them? That they don't add up to 2, they add it to something else. Okay. For example, now this is two walls are here. This is wall number 1, this is wall number 2, and I connected them by beams of flat slab all the way, and I got a certain displacement. Okay. So now in this one, stiffness, the total stiffness of this system is equal to this. It's at the sum of the stiffness of this wall plus sum of the stiffness of the stiffness of that wall. So if I just put one wall and half the load and 2 walls and double the load, I get the same answer, or I get half the displacement. So the 2 stiffnesses are just being added. This is math, right? They are just being added. But if I use engineering and I say, I don't want to put the material like this one, I want to remove all the material from here and combine it together and only put at 2 places, same material. I didn't change anything. I just removed those slab connections from every floor. I added them all together up and put them in 2 locations. So the total stiffness that I had before, I still have the same in terms of the material, in terms of the thickness. I just put them strategically at these 2 locations. And what do I get? I get 1 plus 1 equal to 8. I get 4 times better stiffness, 4 times less displacement in the first one. So my stiffness has increased by 4 times. So I have beaten the math. Now 1 plus 1 is no longer 2, it's now 8, right? That's what we are talking about, that by optimizing the system, by configuration, arrangement, by putting the things at the right location, by strategically locating the material, by distributing things in the most intelligent way, you can increase the effectiveness of the same material. Just like in the previous one, from frame, we put a brace, but the total material was the same. We got a lot better results. But here I didn't even do that. I just simply moved the material from inefficient locations to an efficient location in an efficient manner. And we got this huge advantage from that. So this is what we call beat the math by intelligent material placement and distribution and configurations. Okay, next one. This is the effect that I talk about. And once again, basis of your all systems, most systems in the future is going to be taking advantage of the coupling effect. Because what I did here basically is that right now these 2 walls are independently behaving. I simply coupled them. I made them work together. Before they were just bending independently, just standing side by side and bending, not assisting each other. I just made them work together by coupling them. So by using this coupling effect, now I can increase their response significantly. Instead of having these 2 walls separately acting, I couple them using coupling elements. And same, that frame and that wall acting independently, I couple them. So if we do the coupling effect between 2 walls or one wall and a frame, you will see that the benefits will be much greater than some of their previous stiffness. And that's exactly what we are looking for, beating the math. Wherever we have two components independently, if we find a way to couple them together at any way, at any level, you will find large advantages gained from there. Because this coupling effect, we will see later, changes a lot of things. Okay. So those are the few basic concepts that we can use for efficient structural system development. Another thing that you should remember is this thinking of wall and frame is actually not a good way to look at things, because they are actually continuously part of the same story. So if you start with a wall, for example, and go this way, and you puncture holes in it like windows, then you call it wall with openings, right? This is a wall. Of course, this is solid wall, has a very great stiffness, but I can't use it. I need some openings. So I puncture holes in it and call windows. So I have a wall with windows in it. And then I make the windows bigger. So now I have deep beams and large columns. I can call it large columns and deep beams. I can make it further and I say I have large columns and small beams when the windows become bigger. Or I can say I need full view of the ocean. So I have columns and beams now, right? But the structural form geometry that we started is continuously changing. Just because I start to call it frame, it's not fair, because I'm just putting holes into a wall. Just the size of the hole is bigger now, right? So there's a continuous transition between 0 holes to almost 90% or 80% holes. But the structure is evolving continuously. You cannot change the way you look at it just because the size of something is changing. That means we should stop thinking about them as differences, because you will have trouble defining these 3 systems here. You will have trouble thinking about them, whether it's a large column and large beam or it's a wall with large, small openings. How do you differentiate between them? Where do you draw the line? So please, when you're developing structural systems, think on a continuous scale rather than on discrete scales, right? Think of it, what is the origin of this thing? How can I look at it? If I look at it a frame, I'm looking in a different way. Can I look at it at a wall with openings or something like that, right? So this definition of column and wall is now actually changing. Most designers now do not make a distinction between a column and a wall, because what is it? Honestly, is this wall large column or a small wall? How do you call it? You can call it either way, right? But it changes the way you model it, the way you design it. Column design procedures are different. Column modeling is done by a line element. Wall is modeled by shell elements. Why are you making this? When did you stop modeling a wall by shell element and use a line element? Or when do you stop using a line element, go to shell element? So a lot of engineers now, currently, a lot of people, designers, have stopped making distinction between walls and columns in tall buildings. They think of them as, you can call them piers, vertical piers. Size doesn't matter. They follow the same design principles, modeling, and something like that. Once you do that, you will find that you remove so many issues in your modeling. So that's why I showed you this one, that you can think of them as a continuous. This is, of course, a very extreme case. You can see that the size is very well, though you won't gain much advantage by using shell element, although you could easily do that. And here you can't use frame element. So somewhere there is a gray area. Okay, so that's another part that you should think of. Stop thinking about wall and column as 2 different things, or beam and spandrel. So this is normally called a spandrel. We call it spandrel. If it is a deep beam connecting 2 walls, we call it spandrel. And if it is a beam like this, we call it beam. And then rules for this design and this design are different. They don't need to be. So the distinction between spandrel and beam, and different distinction between wall and column, doesn't need to be made in a tall building context. If you remove that, you will find that many things become easier. Okay, now we come to this interesting commandments. You know what's a commandment? Do you know about 10 commandments? Okay, so religious things, so I will stay away from that. But 10 commandments were supposed to be, given by God to human beings that, okay, you should follow these 10 rules if you want to have a good life, right? So these are the 4 rules for designing a good tall building. Okay, it's not given by God, but okay, we can say it's the rules, universal rules, let's call it them, that you should follow. And if you follow them, you will end up with a good design. Number 1, resist overturning forces due to lateral loads by using vertical elements placed as far apart as possible from the geometric center. It's logical. There's nothing complicated. If you want to stand strong, you have to put your legs like this, right? It's very simple. If I do like this, it's unstable. If I do like this, it's clear. It's very simple, but it's a basic rule. And if you can do that, you have a big advantage against lateral forces, right? That's number 1. Second one, channel gravity loads to the same components. So my gravity load should go to the same legs, right? That I've used for lateral loads. So gravity load system must transfer gravity load to the components which are also resisting the lateral load. That's number 2. Number 3, link these vertical elements by rigid element like this, this portion of the body. The legs alone, if very long, not stable. So they are linked together by a big portion, your core, right? So that's the link them with strong elements so they work together. Resist lateral forces with members axially loaded. So these legs are now compression and tension. So very simple, human anatomy is perfectly suited to resist lateral forces. That's why we're more stable than other things. And we are the only people who walk on 2 legs, right? Because of this stability concept. So it's very simple, but when you apply them systematically, you will always end up with a very good system. And a lot of systems, good systems, ultimately follow these 4 principles. Some follow 1, some follow 2, some 3. Best systems are that follow all 4 of them. Or you can convert a system into one of the good ones. Okay, let's go forward. So this is the simple one. So if there's a lateral load coming, this is the center of the building. The lateral load component should be as far from the center as possible. It's logical, but simple. But like I said, it's common sense. It's appeared common sense. But to apply it is not that easy. Okay. So you must look at these as the primary. Then you should put all the gravity load going to the same components that are carrying. That means no columns in the middle should carry the gravity load. That's the point. It should be the outer columns which are carrying the lateral load also carry the gravity. If you put a column in the middle and that carries gravity load, you are then putting the gravity load in the center on a column which is not going to carry the lateral load because it's not on the extreme, which means you're going to have a problem with those columns. There'll be in tension, right? So that's the other rule. That's why many tall buildings have no intermediate columns. They go directly from the core to the outer column by using longer span decks, longer span floors. Then number 3, tension compression, and these are the components. So we connect them. You remember I told you the connecting elements, the coupling elements. So you use these coupling elements to reduce the shear. So convert them into connected system. Basically couple them to reduce that shear lag, shear deformation. And then everything in tension and compression, gravity plus lateral load going to the same components. So this is just a conceptual framework that you can use now. So when you develop your system, make a matrix and show whether you followed all 4 rules or not. How efficiently did you follow them, right? So now we have covered almost all basic concepts needed to understand and develop basic structural system.